Okay, good morning, everybody. So what we're going to do is first just a little bit of review of kind of the main concept to remind you of how we go from a material science problem to something you need to use the computer for, eigenvalue problem, etc. And then we'll go back to the hands-on after that.
Thanks, William. Good morning, everybody. So yesterday we stopped in the middle of the GW tutorial. So obviously now we can continue that. Before, let me review the last part, which will be then the next tutorial about what William said, how we can basically reduce every physics problem to diagonalizing some Hamiltonian. And this is the case, as we discussed yesterday, of the Bethe-Salpeter equation for excitons, bound electron pairs in optical absorption. You remember we discussed that we want to calculate. This is the tutorial for BSc, the one that is after the GW, okay? You remember we discussed the optical absorption spectrum is given by this expression. And this is the dielectric function of the system, right? So it's a physical quantity and describes the polarization of the medium in response to the absorption of the energy on the electromagnetic wave. And you see that we can recast it in some form, and the only quantities that we need to calculate are these coefficients, the A's, and these energies, these E's, and these come from diagonalizing this Hamiltonian that physically describes the Coulomb interaction between two charged particles, one positive and one negative, two quantum charged particles. And this Hamiltonian, again, contains, and here is where it's written, contains the microscopic details of the interaction of the system. So we have a diagonal part, like if electron and hole will not interact, and then the interaction terms. And these, in turn, can be built using quantities that we compute using many-body perturbation theory. So in the end, the code will just calculate these formulas, the 2 and 3, then put them into this matrix, this big matrix that we discussed yesterday. You diagonalize this matrix, so we go to this equation here, the 4, and we find the energies of the bound excitons, and basically they're eigenvectors. And using these, we can reconstruct the physical quantity that we want. And this is the formula for the spectrum of absorption, optical absorption in this case. But can also be other things, for example, electron energy loss and other even more complicated quantities, for example, Raman spectra and so on. So,
can I add, of course, just small details. Here, what is the final quantity, the spectrum, this epsilon m. This m, do you know what stands for? Because if you go to the kernel of the Hamiltonian, you also there you have an epsilon in the W in the screened potential. So the epsilon m is a macroscopic quantity, so it's an average of the dielectric properties of the materials. The real part provides you the dielectric constant of the material. So this is a scalar. While this epsilon gg prime, this is a matrix, and it is the microscopic dielectric matrix. And usually there is not self-consistency in these calculations. So this epsilon minus 1 gg prime, it is calculated at a level of theory. Usually it's the random phase approximation. Usually is considered only as a static limit. And this is the ingredient that we plug in the Hamiltonian. And then from this W, consider at this level, we solve the Bethe-Salpeter equation. There are also, I mean, in the literature you can find self-consistency that you calculate the Bethe-Salpeter epsilon, not only the macroscopic, but also the microscopic, and you plug in again in the Hamiltonian and so on. This does not guarantee that you get better results anyway. But yeah, just to have this clear, that you have here a microscopic ingredient, and then finally you end up solving the Bethe-Salpeter equation from a macroscopic average. A macroscopic average means, I mean, a reciprocal space is just to take the head of the matrix, the 0, 0 component. Limit from q equals 0, yeah. Yes, sure.
Is this a type of, I don't know if it's the right term, but a generalization that you're going from the microscopic, so I guess you're taking at an atom level, you're going outside to take the whole material as a...
It's no, it's mathematically an average. I mean, you are in a plane wave, and the 0, 0 component in plane wave, it's an integral over the space over the cell. Yeah.
Okay, so so this is one example, as William said, how basically a physics problem, even a complicated physics problem, becomes in a way reduced to linear algebra. Although it doesn't mean that it's computationally easy to perform the calculation itself. Okay, so now basically I guess you can do whatever you want, but as far as I'm concerned, I'll probably go back to where we were yesterday.
We were thinking to actually ask them.
Okay, let's go. I don't know, that's better.
Yeah, so we have two open hands-on exercises you can work on. There's yesterday's about eigenvalue problems, and then also Fulvio can continue with the GW one. So since there's not that many of you, and we have 2 sessions to work through all this, we thought maybe we can vote on this again. So the first choice will be working on the eigenvalue stuff, and then we'll bring Imamura Sensei to the front, and he can talk through it a little bit. Or we can keep working on Fugaku on this GW stuff. That will be option 2. So how many people for eigenvalues? Okay, and how many people for the GW stuff? Okay, and if you want to work on the eigenvalue thing, or you finish, you kind of get satisfied with GW, like definitely go back to that, and Imamura Sensei is in the back there. You can ask any of us questions about this. You can work on whatever you like, or ask even unrelated questions is fine.
Okay, so yesterday we finished just before this section of the tutorial for GW calculations, which takes place in this directory 03, okay? And in this section, really, you will start submitting larger jobs. So actually, this part is organized as a scaling test. So you will find an input there, a submission script, and the submission script inside will have also a small subscript that will automatically update the parallel input variables in the Yambo file. So you will find a gw.in file, which is a standard input. But now the system, we have beefed it up. So it's like a much heavier, although it's always MOS2, molybdenum disulfide monolayer, now it's like with more stuff. So more converged, more K-points, more electrons, and so on. So now it's heavier. You cannot run serially, right? And then with this, basically with this script, you take this input and you just create additional inputs with different values for the possible MPI tasks that you want to assign to the various steps of the calculation. So remember yesterday we discussed that for every segment that Yambo calculates, in this case the dipole matrix elements, response function, the epsilon minus 1, and self energy, it can be parallelized in a different way.
In the final GCPU there is a problem. I mean, if we are calculating, this is for the band structure or for the gap? Because
this is for some QP values, more than one. No, it's okay.
It's okay, but why we are parallelizing over QP?
Because you can.
Of course you can, we are independent, but you are bound on the number of QP you are calculating.
Okay, I mean, it's not, you can parallelize over different strategies depending on your system. So yeah, there's a suggestion for this input, but you can do what you want. And also you can check if it's better to parallelize over this channel, which is the index, the Kn combined index of an energy eigenvalue, or parallelize only of the N band index, which is B here, which is the right index, or on Q point, which I don't suggest at all. So that should not do that at all. So, but the idea here is that you just modify here the number of MPI tasks and the number of OpenMP threads, and then automatically an input will be produced with those numbers and run, and then stored in a separate directory that is recognizable with specific name, including MPI tasks and OpenMP threads, that then you can basically automatically parse and plot and show a scaling plot. Now, for Fugaku, my suggestion is this. So if you open the directory, you will find that there are already two directories pre-calculated. And one is the serial run, and the other is the run with two CPUs. These I pre-calculated them because they are very long runs, because they're not so much parallelized. My suggestion is that you keep fixed the number of CPUs to, okay, let me just open the script, that's better.
While he's doing that, everybody remembers how to get onto Fugaku, right?
Okay, so my suggestion here is this. We discussed this also yesterday. You keep the MPI tasks per node fixed to 4. And in order to increase the tasks, you just increase the number of nodes, right? So the input is already prepared with 1 node and 4 tasks, which you have to submit. And you see here that then the number here, the N CPU will be given the total number of MPI tasks. And the number of threads will be kept constant, and will be 12 for all the runs. So here will be a scaling of just MPI with constant number of threads. And then after you run this calculation basically as is, then you just increase the node numbers. So you go to 2 nodes, which means now 4 times 2, 8 tasks. You go to 3, well, you go to whatever numbers you want and however jobs you want to run. Just maximum number of nodes, do not go over 12. 12 will be the maximum, the largest job that you should submit now. So you can do 1, 2, 3 up to 12. You can do 2, 4, 6 up to 12 as you wish. And then you run all the calculations. And in the end, what you will see that you accumulate other directories. These 2, run MPI1 or MP12, run MPI2 or MP12, is the ones that were pre-calculated. And then you will have run MPI4 or MP12 with the job, if you submit the job as it is. And then you can continue 8, 12, 16, 20, and so on, until the maximum 12 times 4 MPI tasks. And now I will give you time to run this calculation and to finish all the scaling, all the jobs that you want to run. And we will discuss the plot in a little while.
Because if there's left over, we can tell them to submit big jobs at the end.
Yes, absolutely. I don't want to go beyond
There are a lot of hours still allocated.
So, okay, if you want, you can also go crazy, more than 12, but of course the system has a finite size. So you should be careful that you are not parallelizing over channels that are not there anymore. So for example, if I am parallelizing over bands and I have, suppose I have 20 bands, and I put more than 20 tasks on that loop, that's wrong, okay? So, okay, just be careful of that, but apparently you can also scale up. Also consider that
There's 50,000 node hours left, so don't use more than that.
yeah, also consider that since this system is larger than the one from the previous step, but it's still a small system, no, in general. Obviously, the scaling will have a plateau very soon, right? Because there is only so much that you can optimize in a small system. As you try larger and larger systems, then the scaling will be more and more efficient, let's say. Here is a possible plot. This was obtained with a nice layout, but also on another machine. So this is not certainly not the figure that you will get. But I would be interested in seeing what figures of scaling you get. But first run the jobs, then we see how to make this plot. Ci posso prima generare un input con
No, ma qua ce l'abbiamo.
Ok, perfetto.
A remark. I mean, now you try to do this scaling plot, and what you can try to do also is to look how the code behaves, changing the parallelization strategy. The parallelization strategy here is you have for different run level, dipoles, response function, and self-energy, and you can assign tasks on different quantity that enter in the evaluation of the self-energy. And you can check in the cheat sheet what are the variables. And which is the best strategy? This really depends on your systems, but also from your machines. And just to provide an example, for this self-energy, in this self-energy we have a summation over bands. You have 300 bands in your inputs. And then you have to calculate this self-energy for a number of quasi-particle you asked in your input, this QPK range variables. Here you ask for, if I'm not wrong, for 4 or 5 bands and 19 K points in your Berlin zone.
Like 7.
Okay. And let's forget for a moment these Q points because it provides very unbalanced results. But QP and B. So QP, it's a very good way to parallelize your code because for each quasi-particle, you perform the same operation. So these are totally independent, and you can expect a linear scaling, assigning tasks on this variable. B is the summation over bands that you have in each self-energy. And what's better? Well, it really depends. QP is, is linear, but each task have to load and take in memory all the wave functions. So provide an independent calculation, but it's memory intensive, and you can end up that your machine, your single task does not have the memory enough to allow the calculation, you receive a segmentation false. B, it's not linear, there is communication, but you can distribute the memory of the wave function. So what's better really depends. B provides a good scaling. Similar consideration you can done for the chi and for the dipoles. Usually parallelizing on bands, or in this case on conduction and valence bands, because for the polarizability you have to calculate conduction valence pairs. And it's usually a good way to assign on these roles because allows you to distribute the memory of the wave functions, and which are the most cumbersome, the larger work load of memory is indeed on the wave function. So if you have time, you can also change it to try to change strategy. You can monitor your calculation in terms of time to solution and not solve occupied. Has been compiled with the memory.
I think not. If you want memory,
There is an option, but you have to, in compilation, to have a memory profile. But probably there is another way.
Can you bring up the job script?
This is the job suite.
Yeah, the top. I believe it's, if you write this PJM-S, if you're really interested in the memory use, you can put this in the header. It will create a file that has an extension. .stats. This is a Fugaku thing. It's not related to Yambo, but you can then read in there. You can. It's a very long file, but you can find it. How much memory used in the process.
Last thing, of course, you can assign tasks to more than one channel at once. Okay, you can parallelize a little bit over bands, a little bit over key points. The important thing is that the product of all this number equals the total number of tasks that you have available, right? So for this first run of this tutorial, I suggest to keep this fixed like it is, so that you have like controllable scaling plots that you can check. But then if you want to try and see if another setup, like 2 over key points times the rest over conduction and so on, is faster and so on, feel free to try. So as you start running the jobs, changing the node numbers, you should see directories like these pop up. For every job, there will be a couple of directories, and in the names, you will see the number of MPI tasks, which is the thing that you are modifying, and the number of OMP threads, which for this case is constant, but then you can do another scaling test and change it. And so you see 12, 16, and so on. And the maximum I arrived here is 48, which corresponds to 12 nodes. Here I went from 4 to 4, basically, because just keeping 4 fixed in the same node and increasing the number of nodes. So after you have a good amount, let's say, of these directories, we can try a plot. Okay, so if this is happening in your directory, it means that everything is going okay. And you see here that all the inputs that you generate with the script are printed, right? So for each calculation, you have an input that is automatically generated. For example, let's open one of them. So this one I generated by placing 4 nodes. So 4 nodes times 4 MPI tasks per node is 16 total. And then, of course, here I have 16 for this case on the empty states for the dipole. Here 16 on the empty states for the response function. And here 16 quasi-particles, let's say. 16 elements, matrix elements of the self-energy. And so on and so forth. So the other inputs will have the other numbers and so on. For the rest, the inputs are exactly the same. So nothing is changing. It's the same calculation, just with a larger and larger parallelization. So let's start moving to the close of the parallel part. So we will go for the plot. Before that, William just taught me how to do surveillance of your jobs. Apparently, there is a job accounting platform of Fugaku. And here we have the school project. And here you can see the various users ranked in terms of how much they are using the clusters, in terms of node hours, and in terms of number of jobs run. So maybe you can recognize yourself in one of these username numbers, and that's your usage of the machine.
If I could comment.
Yes.
So someday you guys are going to submit, proposals for Fugaku, right? Or some supercomputer. You're going to write your own proposal. It's going to have many people in the project, you're going to get a certain number of hours. And if you don't use all those hours, they're going to get mad at you, right? They're going to say, you asked for 1 million node hours and you only used 10. No, that would be mad. So as manager of the project, you're going to be looking at this dashboard. You're going to be looking at who in your project is doing a good job and who is not. You're going to do this surveillance on them, and you're going to send emails saying, please use more, you know. Just like
Okay, so that's one thing, and yeah. So basically, I think the person that is using more the cluster is this user 10035.
That's me.
No, so it's this one 13578. I don't know if it's a materials track or someplace else. If it's one of you, good for you. And okay, and let's see about these scaling plots now. So if you check in the same folder where you run the calculations, you will see that there is a Python script. This parse y timing.py. So this is just a script to automatically read the report files, find the timing of all the simulations, and plot them in a scaling plot. So it does everything for you, basically. However, you need to visualize the plot. So in order to do this, and also have Python available on the machine, in order to do this, we can use the dashboard that Fugaku provides. If you have Python working with NumPy, Matplotlib on your local machine, you could in principle also download everything. But since we have many different directories with different files, probably it's faster to do in this way. So we go on the dashboard and we go to interactive apps. And here there are several things that you can basically load. But we do the most generic thing possible, and we ask for a virtual desktop here. I don't know if you already know all this or is new. Maybe in any case. And then here we have like all the specification that we want to give. The only thing that we need to change is this system. Instead of Fugaku, we use a pre-post that I assume may mean pre-post processing, right? And okay, then you can select a maximum runtime, but okay, 2 hours is more than enough. And then you can do launch. As you have seen, I have launched many of those, but the top one is the current one. It will start a session, and then it will create basically a virtual desktop. And in this virtual desktop, you can open a terminal. You are on Fugaku on the front end, and you can basically, okay, now it happened, launch desktop. Okay, and perfect. Then from here, I can travel to my directory. I have also all my aliases. I can travel to my, okay, sorry, this is not a terminal. The colors of the directory is clashing with the terminal background. But I can go to my directory and then use things for visualization. For example, you see if I try to type Python.
Make it bigger.
Sorry, yeah. How do I? Control plus. No. Command top. No. Okay. Anyway, so if I do, you see that I have Python. I think is even the latest or most latest. Yeah, I hope it was in a directory more. Okay, 3.12. And okay, so you go in your directory and use Python to run this script, parse_ytiming.py, and it should automatically produce a figure that will also be saved in a PNG format. If you find issues like this plot throws an error, typically it's because some of your calculations didn't complete correctly. Okay, let's see how this can happen. So here I have my runs, and I can inspect one of them. So let's enter one of these directories with the reports. Okay, so, and you see that here we have the usual file that we look at all the time, the report file. And in particular, if we go to the end of the report file, you see that we have timing information, right? So it means this calculation in total ran for 3 minutes, this particular calculation. And you have this timing line in all the reports of all your directories, of all your calculations. So what the parsing script really does is opens this file, checks for this line, and then grabs this value, converts in seconds, and then does the plot, right? So if it throws an error, the 99% is because it didn't find this line, and that means that the calculation did not complete correctly because you didn't go to this stage of game over and game summary. So then you have to find which calculation or which calculations didn't complete correctly, and you have to rerun them, basically, in order to have, or you remove them and you do the plot without that data point. Okay, so in my tests on Fugaku for this exact version of the tutorial, I find this scaling plot. This is produced directly by the script. So I went up to 48 tasks, which corresponds to 12 nodes, with 4 tasks each, as we discussed. And on the y-axis, you have the times of each, the timings that we have seen from the report, extracted from the reports in seconds. And okay, so this you see how basically with small tasks you have a super nice scaling, and then already with very few nodes, since the system is not so large after all, we start already seeing a plateau. Of course, there are many ways to make it scale better. Maybe you have to change, for example, the ratio of OpenMP threads and MPI tasks for this particular system, for this particular application. Maybe in the MPI parallelization, you remember we just did parallelized over one channel, over bands, over quasi-particle indices. Maybe you have to distribute that, and so on. And also, the time to completion might not be the only thing that is important. We mentioned before that memory, most of the times, can be the bottleneck, so one can analyze the memory after the times, and so on. So this is just an example. And of course, Daniele showed the plots of the Yambo scaling at the maximum with a maximum size system, and you can see that if you have a really large system, it can scale over like cluster dimension nodes more or less decently. But yeah, this is more, how you could do a test. Like if you have a system that you want to calculate that you don't know very well, and you want to be efficient because you have to run many calculations of this system, maybe you can first do some tests trying different parallel strategies. And when you are satisfied with the scaling, then is the time to run all the calculations for your production of your data. I don't know if you want to add something. Okay. So before the coffee break, we finish this. So let's see if you can obtain a similar plot, or even if you find something different. And then we go to the coffee break in 5 minutes. So just one reminder: if you find that some plots some simulation did not complete correctly, of course you can check the report. Remember, you can also check the logs. Here you have all the log files for all the tasks, no? And let's just open one to see what is there. You see here, I have all the steps of the calculation, right? For example, here, I have the calculation of the dipoles, and it tells me, okay, I calculated the dipoles in 8 seconds, for example. Remember, the dipoles were parallelized over empty states. Then we go to the response function, and the response function is calculated for each wave vector q, and you have the 1, the 2, the 3, up to the 19, because you have 19 q points in this calculation. And you see after 1 minute, it finished. And then finally, we have the last step of the calculation. You see they are sequential, no, as we said. So every physical quantity then is calculated in sequence. And the last one is the self-energy. So it is the non-local frequency-dependent potential that replaces the DFT exchange correlation potential, and is the largest part of the calculation. And you can see here the steps. And again, in another 1 minute 38 seconds, it completed also the self-energy matrix element here. And now the job is running for a total of 3 minutes, as you can see to the left. If you compile the AMBO also with the memory profile enable, you would have also memory information. And yeah, so here, if your job crashed or stopped, you can actually open the log to see exactly where the stop happened. And YAML can in principle restart in many cases. Like, for example, if it stopped between points 15 and 16, for example, with the 15 completed correctly. This can happen also because the wall time was too low, for example. Then if you rerun in the same folder with the same input, it will start from the 16th. It will not recalculate everything, right? So, because it will first load whatever finds in that folder that you give with -j, and continue with what is not there. So obviously, if it crashed in the middle of a calculation, like if it crashed in the middle of the self-energy, there is no restart from this. You have to start the self-energy from scratch when you run the calculation. But only this part. It will load the previous parts without recalculating. So another point, when you run the script, look here at the tutorial. You have to use Python, but also the script takes an argument. And the argument is the initial string of the names of the directories. So in this case, it will be Python, name of the script, and run_mpi, okay? If you don't put this, it will not check in the directories that start with this string.
Okay, even though you guys are all hard at work, it is the coffee break now. So feel free to go up and take a rest, and then we'll try to reconvene at 10:55.